Hello, let's look at part B. So this one is a little different. So it says, if the incline is rough with a coefficient of sliding friction mu, determine the maximum height to which the block will rise in terms of h and the given quantities. Okay. So this is actually a very similar question as before. But for this question, we're now actually concerned with friction. Okay, so we need to take friction into account. Now, if you saw the previous problem, or part A, you'll know that energy is once again sort of the best way to approach this, right? You could use forces, but then you'd have to just set up an F net, draw that free body diagram, set up your F net to solve for acceleration, and then use that acceleration to find out how far it's going to go. The much easier way is to just use energy, okay? So I have KE, okay? And then at the end I have PE, right, as I discussed in part A. So I start with just moving, and then it's going to go up the inclined plane. But you should notice that I'm actually missing something here, right? There's something that I haven't taken into account yet. And what is it? Exactly, friction, right? So part B is all about friction, and I need to figure out how to use this friction here. And so there's two ways to do this. One is I can say, okay, I know that KE is going to turn into PE, but not all of it is going to turn into PE. Some of it is going to get used up by friction, okay? So if I just put plus work done by friction here, that takes it into account, right? So now I have this PE will be a lower number as this work from friction increases, okay? Alternatively, you could also look at it as KE minus work done by friction equals the potential energy. Both of those are correct and fine, okay? So let's go ahead and plug in. So we have 1/2 mv naught squared. That is our initial kinetic energy. Then we have mgh, capital H, because that's how they define that height. Okay, plus the work done by friction. So that's the force of friction times the distance. Now, distance is not a variable that they gave us. Okay, right? That isn't a variable that they gave us. So we're going to need to figure out a way to get rid of that distance. Okay, we have to figure out how to cancel out that distance in some way. So let's go ahead and draw a little triangle here. I'll move this out of the way. So I got a little triangle. Now my distance, that's sort of this right here, right? That's how far it's moving up the inclined plane. Okay, but I want it in terms of this h right here. Okay. So d is the hypotenuse, right? And then we also know that this is theta. That is a known variable, right? Theta is defined in the question, so that counts as a known variable. And then I know that this would be sine, right? So sine theta, right, because this is the opposite side, is equal to capital H over d. Okay, now this time I want to solve for d, so I'll multiply both sides by d, and then I'll divide both sides by sine theta. So I have d equals h divided by sine theta. Okay, and so I'll plug that in for d, right? Because I don't get to use d in my answer. Okay, so then I go ahead and go to my next step. So I'll have 1/2 mv naught squared equals mg capital H plus ff. Well, I also don't have ff, right? But I can find it, right? So let's draw a little free body diagram. Okay, so this is doing this energy, kind of does end up using a forces stuff as well, right? So mg, okay, and then I have friction down the inclined plane, so that's ff, and then I have fn that is perpendicular to the surface. Okay, there is no force up because it's slowing down, right? It's going to actually be accelerating in the downward direction. Now remember, ff is equal to mu fn. Okay, so mu fn. I know mu, so that counts as a known variable, so I get to use that. But I don't know, whoops, go ahead and undo that. I don't actually know fn, so I need to figure out what fn is. Well, if I break this mg into components, I got a blue component here and a red component, okay? That blue component is going to be mg cosine theta, Okay. Hopefully you kind of remember this from way back in our forces days, but that should be mg cosine theta. So I know that in the y direction, a is equal to 0, which means that Fn will just equal mg cosine theta. Okay, so let's go ahead and write that all out. So I got Ff equals mu mg cosine theta. Okay, so we can go ahead and plug in our next step. So I'm going to write mu mg cosine theta times, and remember my d is this. Okay, so I'll go ahead and plug that in for d. So I have h over sine theta. Okay, so you'll notice that I have an m in every single term. Okay, so I can just cancel that out. And once again, I am solving for h. Okay, so I have 1/2 v naught squared equals gh. I'm going to go ahead and factor out the h. Okay, so I'll have h out front. I'll factor that out. So I will just continue. So I have h parenthesis g plus mu g cosine theta divided by sine theta. And you'll notice that cosine theta divided by sine theta, that's actually a trig identity. So I'm going to go ahead and simplify that. So I have a capital H, g plus mu g cotangent theta. Okay, that's not something you really have to do, but it makes it a little prettier. Okay, but you wouldn't necessarily get taken off points for not making that change. Okay, then we solve for h, so I just need to divide by this right here. Okay, and so then I'll have v naught squared divided by 2, and then I'm also going to factor out this g. So I have 2g 1 plus cotangent theta. And I actually forgot my mu there, so I have 1 plus mu cotangent theta. Okay, and that equals h. And so that would be my final answer for part B.